Okay, last video we did a hypothesis test for means when sigma was known. So now we want to cover the case of a hypothesis test for a mean with sigma unknown. So it's the same four steps. The only difference is we're going to use a t-test statistic instead of a z-test statistic, and we're using the t-distribution to find the p-value instead of the standard normal distribution. Otherwise, same four steps. So, whatever don't let the words confuse you. You're going to get all these different stories, of all these different situations. All you're concerned with is gathering the information that you need to perform the test, right? I mean, like something like this. Manufacturer claims that a new brand of air conditioning unit uses only 6.5 kilowatt hours per day, kilowatts of energy per day. Yeah, I don't, the situation, it can be anything. 6.5, you see the number, that's going to be important. The consumer agency believes the true figure is higher. That's key, because remember, when we form our hypothesis, we're either going to look for evidence that the mean is greater than something, less than something, or different. So looking at both ends of the inequality. Here, this tells us that this is going to be a one-sided test. We're looking for evidence that the mean kilowatts per day is higher than that number. Right? So he runs a test on 50 units and gets an average of those 50 units of 7 kilowatts. That's our X bar. Right? That's our sample mean out of a sample of size 50. And a sample standard deviation. Now, this is the reason why we have to use the t-distribution, because we don't know what the population standard deviation is, so we're forced to use the standard deviation from that sample of 50. And we get a sample standard deviation of 1.4 kilowatts. So now we have the sample mean and the sample standard deviation and the sample size. The question is, should the manufacturer's claim be rejected? And we're going to use a significance level of 0.05, where 0.05 equates with a 95% confidence. So we gather that information. Okay? We know that we're going into the test assuming that this is the truth. Right? Remember, innocent until proven guilty. Our null hypothesis is that the claim is true. The AC units use only 6.5 kilowatts per day. So that's the hypothesized mean. Well, we took a sample. We got a sample mean of 7 with a sample standard deviation of 1.4. We're using a significance level of 0.05, and our sample size is 50. Gather all the evidence. And then just go through your 4 steps. The more of these you do, the more you're going to see how straightforward this is. 4 steps, that's it, every time. First step, what's the question? What are you trying to find out? Now, again, be correct with this. Don't say null hypothesis equals. It's not an equation. It's a statement. Okay? Details, little things, fundamentals, basics. Get those right. It's very important. The null hypothesis, semicolon. The unknown population mean. That's why we're doing the test, because we don't know what this is. We're interested in knowing what this is, but we don't know. We go into the test assuming the manufacturer is telling the truth, and that mean is 6.5 kilowatts. We're running the test to see if it's higher, if it's more than that hypothesized value of 6.5. We were told what alpha level to use. It's a one-sided test because we're just looking for evidence that it's greater than the 6.5. That's what you want to gather in your step 1. Null hypothesis, correctly stated. The alternative hypothesis, correctly stated. The significance level, and what sort of a test it is. One-sided, and we should say this is one-sided to the right because we're looking for values greater than 6.5. So it can be one-sided to the right, it can be one-sided to the left, or it can be two-sided if we really have no idea where, which end we're looking. And that involves something else we'll get to in another example. Okay, so step 2, we do not know sigma, so this will be a t-test statistic. And remember, the t-distribution differs slightly depending on each sample size. So a sample size of 50, remember, gives us degrees of freedom of n minus 1. So in this case, 49 is going to be our degrees of freedom. Our t-statistic is the sample mean minus the hypothesized value. Now, the only thing that differs between the t-statistic and the z-statistic is this right here. Remember, for the z-statistic, that was sigma. We don't have sigma. We have to use S, and that's why it becomes a t-statistic. So we perform that calculation. We get 7 minus 6.5 in the numerator, and 1.4 divided by the square root of 50 in the denominator. We calculate that value, and t-statistics to 1 decimal, remember, z-statistics to 2 decimals, because that's the way the tables are set up. So 2.5 is what we get for our t-statistic. And we round that to tenths, 2.5. All right? So just like in the z-test, we're saying if this is true, we're getting a value relatively 2.5 standard deviations, not quite again because it's a t, not a standard normal, but pretty far away from the center of the sampling distribution, which would be this if the null hypothesis was true. All right? So again, remember the question. If this is true, what's the probability that we get a value this far away from that? Right? Is it common? Is it like, well, yeah, you're going to get that a lot, so it doesn't surprise you, and you stay with what you thought. But if your value only happens a small percentage of the time, then you're going to think, well, maybe this isn't true. We'll go with the alternative. That's the whole logic behind the test. So we find the p-value. In this case, again, one-sided to the right. So we're looking for the probability of finding a t in a t-distribution with degree of freedom. We're going to use 40. Remember, we said our degree of freedom was 49. Where is it? Where did I put that? Degree of freedom is 49. So our tables go from 40 to 60. Between 40 and 60, always take the lesser if you have to make a choice. So we're going to use degree of freedom 40 in the table. It's just because they don't give us all the numbers between 40 and 60. Always use the lesser number that is the best choice. So we look in the table, and we'll go and look and show you where to look. Greater than 2.5, and we're going to see this number 008. So let's go to our table and see where we find that. So you go to your tables. This is the standard normal table. We're not using that one this time. Remember, this page gave us t-critical values for our confidence intervals when we were forming confidence intervals for means and sigma unknown. And now this is the first time we're going to use the actual pages for the t-distribution. Now the t-distribution is a bell curve. As you can see, basically it's very similar to the standard normal, except there's more areas on the ends of the curve and less in the middle. But it's still a bell curve. It's still symmetric. Still the total area equals 1. But notice this table gives us the area to the right of the number that we're looking up. Whereas the standard normal, recall, gave us the probability below or to the left of the z value that we looked up. So be careful, again, details, little things, basics, fundamentals. This table gives you probabilities above or to the right of t. So we're looking up, what was it, 2.5. So this table gives us numbers to tenths in the left-hand column and degrees of freedom across the top. So there's several pages for this distribution. Notice the first page here takes degrees of freedom 1 through 12. I just noticed that the second page is identical to the first page, so just ignore that. Sorry about that. But the third page then continues the degrees of freedom starting at 13 and going up to 24. And then the next page gives you the t distribution with degrees of freedom starting at 25, going up to 30, and then it starts jumping 35, 40, 60, 120. So remember we said if you have to make a choice, choose the lesser number. We had 49, so we're going to choose 40 degrees of freedom. We're going to go to 2.5 on the left-hand column over to 40 degrees of freedom, and we see that number 0.008. These numbers are a little faded. If you can find a better table, again, please let me know. There's other t tables, but you have to read them, and I think they're much more difficult than this table. And you can kind of, I think you can make out all these numbers, and you can kind of see the progression, right? They get larger at 0.5, and then they keep getting smaller and smaller and smaller. So I think you can easily make out all of these numbers, even though they are a little faded and blurry. So 2.5 under 40 degrees of freedom gives us our p-value of 0.008. All right, so that's the number we have here. So that's a very small number. So again, let's go through the logic again. The logic says if this is true, we're going to get a number this high only this percentage of the time, right? Because if this is true, this is the center of the sampling distribution, and that's what we're comparing our sample mean to, right? We had a sample mean of 7, and we're comparing that with the infinite number of samples of size 50 that we could take from this population theoretically. If this was true, this would be the center of that sampling distribution. And if this is true, we would get a value this far away from that only, what is this? This isn't even 1 out of 100 times, right? This is 8 out of 1,000 times. So that leads us to believe our p-value is less than our alpha level. So we reject our null hypothesis. We think, well, maybe this isn't true. Right? Maybe it isn't true if what we got only happens 8 out of 1,000 times. So maybe it's not true. So we reject the null and we say there is sufficient evidence to suggest that the AC units use more than 6.5 kilowatts, which was our alternative hypothesis. All right? So I'll try to do several examples of different types of hypothesis tests. We've done one for means when sigma was known. This was sigma unknown. We'll do the greater than, the less than, the double-sided test just to show the difference there. And then we'll get into hypothesis tests for proportions. All right, good times.